Today we will discuss the MOS inverters. In MOS inverter, we will discuss the static characteristics. So inverter is the most fundamental logic gates that perform a Boolean operation on a single input variables. Any circuit can be in any circuit we require the inverters. So inverter is the most fundamental logic gates. It will be seen later that many of the basic principles employed in the design and analysis of the MOS inverter can be directly applied to more complex logic circuits such as NAND gate and NOR gate as well. So in the MOS inverter, we calculate VIL, VIH, VOL, VOH and VTH. So we calculate all 5 parameters, and all 5 parameters can be directly calculated for the complex logic circuit such as NAND gate and NOR gate. This is the symbol of the inverters, where we apply the input A and we observe the output B. Output B is just the complement of the input A. That's why its name is inverter. So this is the table of the inverter. This is when the logic 0, then output 1, when the input 1, output 0. And this is the voltage transfer characteristics of the inverter. This is the input and this is the output. So if the input range between 0 to VDD by 2, then it is treated as a logic 0, and if the input is 0, then we get the output is 1, so means equal to VDD. So this is the threshold voltage VDD by 2. If the input is less than VDD by 2, then it is treated as a logic 0 and we observe the output 1. If the input is greater than VDD by 2 but less than VDD, then it is treated as a logic 1, and if the input is 1, so output logic is 0. So this is the voltage transfer characteristics of the ideal inverter, and it is different from the practical inverter. So in this there is the sharp, in this case sharp degradation. It VDD by 2. At VDD by 2 instantaneously changes output from 1 to 0, but in practical inverter it is not observed. In practical inverter, slope gradually decreases with the finite slope. General circuit diagram of the CMOS inverter. This is the general circuit diagram of the NMOS inverter. This is the driver transistor. This is the load. Here we represent the load by the black box. So load may be resistor, may be depletion type MOSFET, may be enhancement type MOSFET, may be P type MOSFET. So depending upon the load, the characteristics of the inverter will be changed. So basically characteristics of the inverter mainly depends upon the load, types of the load and the characteristics of the load. So the input voltage of the inverter is also the gate to source voltage. This is the driver. So gate to source voltage. This is the gate terminal and this is the source terminal. So the voltage between gate to source is treated as the input voltage. So input voltage is equal to the VGS. The output voltage of the inverter can be treated as voltage between the drain and the source, VDS. So this is the output voltage. So the output voltage of the circuit is equal to the drain to source voltage. Output voltage is equal to the VDS. Source in this circuit, we assume that the source and the substrate terminal of the NMOS, also called the driver transistor, are connected to the ground. So VSB equal to 0. The generalized circuit representation, load device is represented as a two-terminal circuit with terminal voltage VL and the terminal current IL. The characteristics of the inverter circuit actually depends upon the type and the characteristics of the load inverter. So the characteristics of the inverter depends upon the types of the load and the characteristics of the load. The output terminal of the output terminal of the inverter is connected to the input of the another MOS inverter. So this is the output terminal of the inverter. It will be connected to the input of the another inverter. So consequently, the next circuit seen by the output node can be represented as the lumped capacitance. So this is the lumped capacitance due to the next inverter. Since the DC gate terminal of the MOS transistor is negligible for all practical purpose, so there will be no current flow into or out of the input. We know in the any MOSFET IG current is equal to 0, so there will be no current flow into or out of the input. Voltage transfer characteristics. This is the voltage transfer characteristics of the inverter. This is the resistive type. Here we replace the load by the resistor. And this is the voltage transfer characteristics of the practical inverter. In the practical inverter, we observe there is gradually decrease in the output voltage. In the practical inverter, in the ideal inverter, it is sharply decreased. But in the practical inverter, it is gradually decreased with the finite slope. Here slope is -1, here slope is equal, again here slope is -1. So this is the input line and this is the output. There are various parameters: VOL, VIL, VIH, VOH, VTH. So by the KCL law, ID current equal to the IL current, means drain current equal to the load current. Since there is no current in this path, so ID current equal to the IR current. Voltage transfer characteristics describing the output voltage as the function of input voltage under the DC condition. So this voltage transfer characteristics describing the output voltage, this is the as the function of input voltage under the DC condition. Upon the examination, we can identify a number of important properties of this DC transfer characteristics. There are, however, several significant difference between the ideal inverter and the practical inverter that deserves special attention. So for the very low input voltage, output voltage is equal to the high value of VOH. So if the input voltage is low, then the output voltage will be high. In this case, for the low input voltage, driver transistor, this is the driver transistor in the cutoff mode and does not conduct any current. So if the driver transistor in the cutoff mode, so ID current is equal to 0, and we know output voltage is equal to the VDD minus voltage drop across this resistor. So if the ID current will be approximately equal to 0, then voltage drop across this resistor will be, means VR equal to the approximately equal to 0. So output voltage must be high. Output voltage is high. As the input voltage increases, driver transistor starts conducting, and if the driver transistor starts conducting, ID current will be increasing. So voltage drop this resistor will be increases, and as the voltage drop across this resistor will be increases, output current will be starts decreasing. Notice drop in the output voltage level does not occur abruptly, such as the vertical drop assumed for the ideal inverters voltage transfer characteristics, but rather gradually with a finite slope. We identify two critical points on this curve where the slope of the voltage transfer characteristics equal to -1. There are two critical points. One is this and another is this. The smaller input voltage value satisfying the slope equal to -1 is assumed as a VIL. This is the smaller value where the slope equal to -1. We assume VIL. And other larger input voltage satisfying this condition, means slope equal to -1, assumed as the VIH. Both of these Both of these voltages play significant roles in determining the noise margin of the inverters. Both of the points VIL and VIH play the important role in calculating the noise margin. We will see noise margin in the next slide. As the input voltage further increase, the output voltage continue to drop and reach the value of VOL. When the input voltage equal to the VOH. So when the input voltage is equal to the VOH, output voltage is equal to VOL. As the inverter threshold voltage VTH. So as the input voltage increases, output voltage will be decreases. The point comes where the both input voltage and output voltage both are equal. That voltage is called threshold voltage. Means the threshold voltage where the input voltage equal to the output voltage, and at which point slope equal to 1. So this is the point at which input voltage equal to the output voltage and slope equal to 1. So thus total 5 critical voltage we have to calculate: VIL, VIH, VOL, VOH and the VTH. VOL, VOH, VIL, VIH and the VTH. So VOL, VOH, maximum output voltage when the output level is logic 1. VOL, minimum output voltage when the output level is logic 0. VIH, maximum input voltage which can be interpreted as a logic 0. And VIH, minimum input voltage which can be interpreted as a logic 1. Noise immunity and the noise margin. So in this case, three inverters are connected in cascade with the interconnect wire. So this is the first inverter, this is the second, and this is the third. And first and second is connected by the interconnect. Suppose we apply the VOH output. So this is treated as a logic 1. So we observe VOL means logic 0. So by the interconnect will add some noise in the output. So output voltage may be increases or decreases. So if we assume that output voltage will be increases, and if this VOL is greater than VIL, so we know VIL is the maximum allowable voltage which treated as a logic 0. So if it is VOL greater than VIL, then it may be treated as a logic 1. So it will generate the noise. So the separation between the VOL and VIH must be high. This is the graph of the noise margin. This is the input. This is the output. This is the VOL. This is the VOH. This is the VIL, and this is the VIH. So this noise margin can be calculated as the VIL minus VOL, or the noise margin also can be calculated as the VOH minus VIL. So if noise margin added, so if it is greater than VIL, then it cannot be treated as a logic 0. So it will add the noise. Now in the next slide, we will discuss the resistive load inverter, which is the special types of the general resistive load inverter. So this is the circuit diagram of the resistive load inverter.